Yes, thank you everyone for coming, and it was great to be here visiting Taiwan and ASIAA for the first time. Yes, so the talk will mostly be about the astrophysics of galaxy cluster. I have one slide for cosmology because I know there's a lot of cosmology here, so I have to at least have one slide on cosmology, but mostly it will be most about the astrophysics part of the galaxy cluster. Yes, so let's get starting. So yes, as I was introduced, so my name is Taweewat, and then the talk is about one specific galaxy cluster called CHIPS1911+4455. If you want to know what the CHIP stands for, I'll leave that for question, because so somebody have some question to ask. Okay, so yeah, just like I was introduced before, so yeah, so I'm a lecturer at Chulalongkorn University, starting at the end of 2023. So I've been there for 2.5 years now. Oops. Yeah, not me, right? Okay, good. And that is Chulalongkorn University, if you haven't seen it before. So it's located in Bangkok, Thailand, the center of the city. So actually, if you zoom out a tiny bit more, it will be all tall building. But the university is so old that there are not tall building there yet. But if you zoom out a little bit more, there are tall building nearby. And that was me doing some observation in optical with the Magellan telescope in Chile. And it's just what I was introduced. So I work in the galaxy cluster first with Michael McDonald on like a feedback in galaxy cluster with at MIT, and then did the postdoc at Stanford with Steve Allen. Okay, so I think a lot of people here know what a galaxy cluster is, but I'm just going to give you a really quick introduction. There's only two components. There's a member galaxy and the BCG. So the member galaxy are all the galaxies that are part of a galaxy cluster, but it's not all the galaxy in the picture. So if I can point out, so all these other galaxies that look really nice, like all these spiral galaxy, they are not a member galaxy. Only the one that have the similar colored like a red and red color here are the member galaxy. And there is a lot of people working on trying to identify what are the member galaxy, how to get where are the cluster member are, and how what are the cluster is. But the most important galaxy in all the galaxy is the BCG. Well, for me at least. Some people have some other favorite galaxy. But the BCG, or the brightest cluster galaxy, are where the center of the cluster is located. So usually when we talk about galaxy cluster as a whole, it's like a giant big dark matter halo with a ton of stuff inside, many galaxies, many hot gas and everything. But usually the BCG is where the center of the gravitational potential well is, which is located. So if we find the BCG, then we can hopefully find the center of the cluster. Okay, I'll tell you a quick story about what did we understand about galaxy cluster right now. So we know, like we see from the previous slide, that almost all the member galaxy are red and dead elliptical galaxy. So like you can see here, all of these are elliptical galaxy that red and dead. And then especially the BCG is extremely red and extremely dead. So it doesn't have a lot of star formation. In fact, it doesn't have, it usually have no star formation at all. And that is interesting in itself. But the most important thing about a galaxy cluster that a lot of people are interested in is the X-ray extended emission here. So here is the image of, Here is the image of BCG of the galaxy cluster here. So here is one galaxy cluster. The BCG is like here. And at the same exact scale, you can see here are all the X-ray emission. So the X-ray emission of the hot gas is extended from the center all the way to the outskirts of the cluster. Well, it doesn't go all the way out because it's too faint. And then on the right-hand side, that's what the SC signal looks like in the CMB. So the galaxy cluster can also be detected using the CMB signal called the SC effect or Sanya-Sodowich effect. But I'm not going to talk about that today either. Okay, so and then from the hot gas, so we know that the gas temperature of the ICM is roughly 10 to the 7 Kelvin, so 10 million Kelvin gas. From that you can actually estimate, because that gives you the thermal pressure, and then that can tell you what is the hydrostatic equilibrium mass, or what we call the total mass of the galaxy cluster as a whole. And the roughly order of magnitude for the galaxy cluster for us is roughly 10 to the 14 to 10 to the 15 solar mass. Maybe like 10 to the 14 on the small side, and 10 to the 15 is like a massive cluster. Okay, so I like this slide because it tells you a lot about this one telescope called the Hitomi, which is Japanese X-ray high-resolution spectroscopy that was launched in 2016-17, I believe. So what it does is it tries to understand what the gas look like. So here is the hot gas, and then we try to measure what is the velocity dispersion of the hot gas inside the galaxy cluster, because from the X-ray imaging we can only get the average temperature, like but then from the high resolution X-ray spectroscopy you can get the strong emission light here, and that tell you the velocity dispersion of the gas, which give you the information about the turbulence, or how much the gas is moving around and create all this turbulent pressure or turbulent heating. But what we found in this observation, and at first time ever in 2016-17, is that the emission line is extremely narrow. It's so narrow that it's like super peaky here, and that means the turbulent velocity or the velocity dispersion of the gas inside of this typical cluster are extremely low. So there are not much turbulent pressure to support all these hot gas. So that means that the hydrostatic equilibrium, or just equating the thermal pressure with the total with the gravity, is pretty much close to correct for some certain cases. Okay, but unfortunately, if you have heard, Hitomi was only last for a couple months, and then it was no longer with us. That was one of the very exciting results that came out of the telescope. So a couple years ago now, there is a new telescope called the CHIPS, which is pretty much similar to Hitomi, which is extremely narrow or like high resolution X-ray spectroscopy to get even more measurement of the gas temperature inside the hot gas. So now, instead of just one giant pixel, the pixel is pretty big. Now you can get, okay, so the background image here coming from additional X-ray observation from Chandra, but the measurement that we're talking about here is all this square here. So these are like one pointing. So with multiple pointing, you can get the measurement of the turbulent velocity, or like the velocity dispersion of the gas at specific location of the cluster. So you can measure the velocity dispersion of the gas inside the center, in the outskirts, in between. And what we found is that the velocity dispersion is actually higher in the center because of some feedback is going on, making the gas moving very fast, create all this extra velocity dispersion. And the velocity dispersion is actually very high in the outskirts because of some like merging event or like activity in the outskirts that are creating all this movement of the gas. But it's very interestingly, the velocity dispersion is extremely low in the center, in the in-between phase, which is what they found surprising in the result that just came out in CHIPS recently, and that is one of the main results that they have learned so far. And then right now, CHIPS try to observe additional clusters, so now maybe like up to 10 different clusters now that they're doing this observation, and they give out roughly the same number of velocity dispersion. So like 150 maximum at 200 kilometers per second. Okay. So those are basically the general idea of how the hot gas works and where it is, and what can we learn just from looking at the hot gas alone.
what is the corresponding non-thermal pressure
Yeah.
distribution?
So for this, I believe the non-thermal pressure is just a few percent. Like, yeah. Yes. Okay. So that is our understanding of the gas. So what is going on after that? So what people have been trying to understand is that what happened to the BCG or the actual galaxy, the central galaxy, because it doesn't have a lot of star formation. It doesn't form many new stars. It doesn't do much. And yet it seems like the X-ray hot gas still remain very hot. The question is, why is the X-ray hot gas can remain that hot for such a long time without actually cooling from the radiative cooling that is pushing out all the energy outside? And what we learned is one of the solutions that people propose to stop the cooling from happening, what called the agent feedback. So here is my one slide introduction of agent feedback, and here is the the famous galaxy cluster MSO735. Here is the visible image of the galaxy. Here is the X-ray, and here is the radio. In the X-ray, you can see the extended hot gas, just like what I showed you in the couple slides already. But the interesting thing is there is a gap here, like a circular gap here. In the X-ray, we call that a cavity. But then if you observe it in the radio, you can see the emission of the radio coming from here and here, which they believe is the AGN jet that coming from the supermassive black hole in the center of the BCG. So a tiny dot inside the BCG, like so here the BCG, the black hole is inside of that, and the jet is so much bigger, and it's creating all this red emission in the radio. And then when they mash the two together, they found that the radio jet is what causing the cavity to happen. So like the energy from the radio jet is actually push out the gas and create this giant cavity. And that giant cavity is what we observe in the X-ray. And when you calculate how big the circle is, you can kind of estimate how much the energy have to put into the system to create that big of a cavity. And that big of a cavity, that amount of energy is roughly equal to the amount of energy that is needed to heat up the gas and make the gas remain as hot as 10 to the 7 Kelvin gas up until now. So our understanding right now is that the agent feedback is a lot responsible for stop the cooling from happening. Oh yeah, another effect is it also stops the cooling in the BCG and almost stop all star formation from happening near the BCG, and the growth of the galaxy in the of the BCG is mostly probably likely only grow via merger with the member galaxies. And yes, so the gas is depleted because of the jet, the star formation is quenched, stop star formation from happen, and the merger is what caused the star, and the merger what caused the BCG to grow. Okay, so I'll give you an example of what a BCG look like if you like to look at a lot of images. So here is an example of 100 different clusters, more than 100 different clusters, and each one of these is a BCG. And as you can see, almost all of them look like a dead elliptical galaxy with not large amount of star formation. In fact, it's like if we calculated the star formation rate of almost all of this galaxy, the number is roughly about less than it's roughly on order of a few. So like 1, 2, 3, 4, 5 solar mass per year. Each a typical star formation of this BCG, which is not surprising because it's an elliptical galaxy. It doesn't usually have a lot of star formation anyway. Okay, I have one slide on cosmology, and it's this slide. So why is it important? And it's the reason that the reason that galaxy cluster is interesting for cosmology is what called self-similarity. And so what I've been explaining so far is BCG have pretty much the same property, the red and dead galaxy. The member cluster look pretty much the same in almost all galaxy cluster. The metallicity is almost also pretty much the same in almost all the cluster when you measure it in the hot gas. And then the gas profile fraction or here, which is tell you how much the hot gas is divided by the total mass, is roughly equally the same at the especially near the outskirts. From like, so here is the gas fraction profile. So here the gas fraction, that's 1%, 15%, and here is center of the cluster, and here the outskirts. And then you can see that near the outskirts, usually the gas fraction is roughly the same in almost all the cluster. And then it's also similar thing happen also for the entropy profile. I will talk a lot about the entropy profile later, but from what I try to explain here is that almost all the cluster have pretty much the same outskirt property in all the galaxy cluster. And then they also have very low star formation rate. And all of this property is very, very good for cosmology, because in cosmology we want everything to be very similar. And then that will not, so the astrophysics part of the galaxy cluster will not have too much impact on the result that we get from cosmology. Yes. And then I'm not going to talk about cosmology anymore, so because that's all I know too. So let's move on. So I'll give you one example of what a typical galaxy cluster look like. Here is SPTCL JO1417. 0417, sorry. And the name suggests that it's a SPT cluster, so it's first detected by the SPT survey, and CL means cluster, and that's just coordinate. Here is an example of an extremely massive cool core cluster with a quiescent BCG. So we estimate the redshift of the cluster to be 0.58. We get the mass 5 times 10^14. We detected a strong cool core. We have a relaxed ASIAA morphology, so the X-ray look pretty much circular with not much going on. And we did not detect any star formation, so the optical spectra give just the upper limit on the detection of less than 3 solar mass per year. And here is the BCG. Yes, it just looks like a red galaxy. Okay. So I'll give you, I'm going to show you many plots that look like this. So I'm just going to introduce it again. So here is the radial profile. So here is the center of the cluster, and here is the outskirt, center of the cluster and outskirt, and for 4 different properties: density, temperature, entropy, and cooling time. The black is the data point coming from this specific cluster, and the blue are an average profile from all the lilac cluster. So you can see almost all lilac cluster have a pretty similar profile with this cluster. So like the upper part here look very similar on almost all of them, and the density and the temperature as well. But the temperature here is a bit high, the density is a bit low, making the entropy a bit higher and the cooling time a bit higher. And that might be the reason why there are not much star formation happening in this cluster. And the reason that it is interesting is because we have been looking for a lot of clusters that just start to have some star formation. Okay, so yes, so I was just talking a lot about galaxy cluster with no star formation, so the BCG and red and dead galaxy, but there are clusters with couple exceptions. Actually, there are more than, so here are just example of objects that I just show here. There are a lot more of this, but roughly on order of 10, 20, 30-ish out of like 1,000 or like 100 or something. But yes, so even though I've been talking about cluster with no star formation, but here are examples of cluster with a ton of star formation. In this paper, what he did is he observed the Hubble observation with a narrowband imaging for oxygen 2 and try to see how much oxygen 2 it is near the BCG. And you can see all this cooling or star formation that is happening in each of these BCG. And it's definitely not dead and dead in most of these cases. So let me introduce two of the famous galaxy cluster, which is Phoenix and H1821. Phoenix cluster is a starburst hosted cluster. When I say starburst, I'm saying the star formation rate is 600 solar mass per year. We were talking about 1, 2, 3, 4 solar mass per year. So these are 100 times bigger than a typical galaxy cluster, BCG. And here is what the BCG look like. The BCG look like this, but then there is this cooling or like cooling flow or cooling filament or whatever you call it that are forming a ton of new star. And this new star is what we have measured here in star formation rate. If you observe in the X-ray, you can also see this thing called the density in the core. So I'm just going to show you here. So yeah, we just measure the density in the core here. And it's also 10 to the minus 1 or 0.1, which is extremely high for a typical galaxy cluster. And then the relaxed morphology, because the X-ray look like a very circular or spherical shape, which is mean it doesn't have been disturbed previously. Okay, so those are one of the famous one. Another famous galaxy cluster is H1821 or the quasar-hosted cluster. So now not just star formation, but this guy have a giant AGN in the center. The AGN is so bright that it looks like a star. So in order to actually look at the host galaxy, you have to remove all the light from the AGN, which is extremely difficult. And I'm not doing that, some other people doing it. It was a lot of work to just remove the emission from the AGN to measure the star formation of the galaxies inside of it. And we think the star formation is also about 120. And accretion rate is roughly about 40 solar mass per year, estimated from the brightness of the AGN. And again, it's also in a relaxed, simple morphology of the galaxy cluster. Okay, so I'm just tell you a big introduction about what a galaxy cluster is, what are typical galaxy cluster, and what are not so typical galaxy cluster. So now let me introduce the cluster for today, which is CHIPS1911+4455, which is a galaxy cluster that I have been studying for a while now. Okay, so let's start the actual talk now. Okay, so CHIPS1911+4455, I'm gonna call it a cooling flow in a merging cluster. The cluster redshift is 0.485. It was discovered by the CHIPS survey in 2021, and then the main property in the X-ray is that, I'll show you the X-ray image in the next slide, is that it have a very strong cool core cluster in the X-ray, but the morphology in the large scale morphology of the ICM or the X-ray emission is not spherical. It's actually extremely elliptical or like disturbed. So we call it a highly disturbed morphology. And then if we measure the star formation rate of the BCG here, we measure the star formation rate of roughly about 140 to 190 solar mass per year, which is also extremely high. Actually, one of the highest star formation rate ever detected. Well, Phoenix is the highest, and then there are a few more, and this is one of the higher one. And then with the Hubble observation, you can see that the filament is roughly on the order of 30 kiloparsec scale observation. And then I don't see any sign of optical AGN in the spectra that we have observed. Okay, yeah, so that is a quick summary of a galaxy cluster called CHIPS1911, and I will just gonna go back and tell you more about how did we find it and then what did we learn from it along the way. Okay, so here is the first discovery image of the galaxy cluster using the pan star. There's a long story before how did I get to this specific object, but the key is I'm looking for different optical data set, and then I found this object as a new galaxy cluster because no one had called it a cluster before. The main property that you can see in this galaxy cluster is that each of these dots is a member galaxy which have a pretty red and dead color, yet the BCG is having a completely different color. The color of the BCG is so bright that is almost the reason that nobody has found it before is because the BCG doesn't look like a BCG at all, and nobody actually bothered to claim it to be a BCG of the cluster. But with additional observation from the Hubble with higher resolution imaging, then you can actually see that the BCG or the host galaxy that are the elliptical galaxy look pretty much the same color and property than a typical member galaxy nearby, except the part that they have this blue fragmentary structure that are extended up to the south here, and then there are a tiny bit up to the north. And then these two main components are what make this white, really bright white color in the first optical image. Okay, so with that information, then we go to Chandra and ask for X-ray observation. So here is what a Chandra X-ray observation look like. Here is a 30 kilosecond observation. You can see the contour, this is the contour plot of the X-ray emission. The peak is here. The BCG located at the location here in the peak, and yet the large scale morphology is very unsymmetric. So that there are more dense area here, and then there are much further or extended out to the right hand side here. So we call it a highly asymmetric system with a strong cool core. And then at the end of the talk, I will show you the new data that we just got. We got in 2023, we got approved additional data from Chandra to observe this object, and then the preliminary result will be presented at the end. Okay, so let's just talk about the first 30 kilosecond of data first. And if you want to know how long kilosecond is, I don't know. You can figure it out. I don't know why the X-ray people use kilosecond as a time unit. Okay, so the first thing we do when we get the data like this is to quantify the morphology of the emission of the X-ray. And then the two main parameters that is important for galaxy cluster morphology in the X-ray is called the peakiness and symmetry. So the peakiness tells you how much the light or how much surface brightness it is in the center of the cluster compared to the outskirts in the X-ray. So now I'm not talking about the BCG anymore, I'm only talking about the X-ray emission. So if the cluster is very peaky, that means almost all the light is coming near the center, and then the outskirts have a lot less light. But if the cluster is not super peaky, then the core itself is not super bright, and it's getting flattened earlier than other clusters. Okay, so we call that peaky cluster, but the official name of it is called the cool core. It's called the cool core cluster. And then we call the non-peaky cluster the non-cool core cluster. Okay, the second property that we use is called the symmetry, which tells you how much disturbed or symmetric the image of the X-ray look like. If it's symmetry, it looks like this. So we draw an elliptical ellipsoid here. And then if they are aligned in the same thing with a pretty much symmetric object here, then we call it symmetric. We call this cluster symmetry. And then if it's not perfectly aligned, or like it have some different orientation of each of these ellipsoid, then we call it symmetry. The official name for the symmetry object, we call it a relaxed cluster, because it looks like it has not been merged with other cluster before. And then the official name of this, we call it a disturbed cluster, because it has been colliding with other cluster before. Okay, so here is a plot of all the cluster that people know so far based on this work. And then you can see almost all the cluster along this axis, well, ish. So a lot of clusters are disturbed and non-cool core, and a lot of clusters are relaxed and cool core. So these are usually the main property of the cluster is if it's relaxed, it should be cool core. And if it's disturbed, then the disturbance of the cluster should destroy the cool core or reduce the cool core or make the cool core smaller. But the CHIPS1911 are like here. So it's one of the unique objects that cool core cluster, meaning it's peaky, yet it's not symmetric or it's in the disturbed morphology. Okay. Okay, so yeah, so the first thing that we did after we get the data, we identify the morphology, and then the second thing that we have to do is to get the profile. So here is the density profile, and here the temperature profile. The density profile, like the previous slide, here is a very peaky temperature or density profile, and then here is a strong cool core temperature in the center. So the reason that it's called cool core is because the core is cooler than the outskirts. Yeah. So the temperature in the core is roughly about like 3 to 4 keV, and then the outskirts is roughly 8 to 10 keV. And then so yeah, from that, from the density and temperature, we call it a cool core cluster. Yes. Okay, and then the second property or profile that I want to talk about is called the entropy profile. And the entropy profile is technically it's not entropy in the sense of the statistical mechanics. So in the paper we call it a pseudo entropy, but I'm just gonna call it entropy because I keep saying pseudo entropy forever. It takes a lot of time. It's basically measure how much is the heat content of the gas is available for the gas at different radius. So here is a profile of, so the black line here are the profile of a typical cluster. We use an exact sample of the cluster. And then the purple line here are the entropy profile of the Phoenix cluster, which is the most unique cluster that we know of, with 600 solar mass per year of star formation. And you can see the entropy of the gas near the core of the cluster is extremely low. And that match what we saw in the optical, because we see all these cooling filaments that's coming in near the BCG or the center of the cluster, and that means there are not much heat, or that the heat content of the gas is not much in the center. And the CHIPS cluster is the orange line here, which is pretty similar to the Phoenix cluster. It's pretty much follow all the way here, and then we don't have enough data to resolve all the way down to like a very few kiloparsec here in the center. So we just stop it here. So it's one of the lowest core entropy property in the center, a core entropy in the, compared to all the other except cluster. Yeah, yet and then but the outskirts look pretty much the same with all the other cluster. Okay, so let me give you a quick interpretation of what we learned about the CHIPS cluster in 2021. Which is, we think what is happening is that there is a merger trigger event, or like this cluster experienced some merging event in the past, but the ICM or the hot gas is still remain disturbed from that merging event. It displaces the core entropy gas near the center and make this like longer extended core here, and then that could potentially delay the agent from happen. When there is no agent, that means maybe they can have some star formation. So because of the core gas is got moved by the merger, it delayed the agent feedback from happening, or the agent is not happening at the location of the center of the cluster or the peak of the ICM, and then that maybe allow star formation from happening. Okay. Yeah, how was everyone so far? So now I'm just finished 2021, and we have 5 more years to go. Yes, from now I will present it other people work now based on this object. So after 21, when we published this paper, there are other people who are doing completely different wavelength of study. So yes. So actually they are in 2025. So in 2025 there are 2 different work by 2 different groups who are working on this galaxy cluster. One of them using sub-millimeter observation, and the other one used radio observation. And then, so this second half of the talk, I will talk about what did we learn after that 2021 and what we think is actually happening now in this specific cluster. Okay, so let's go through two of these papers together. The first one is called sub-millimeter observation. Yes, so sub-millimeter observation, this one is because of the object. If you notice, the object is extremely not, like plus 44, 55. The plus 44 mean that almost impossible to observe by any fancy telescope in the south, like ALMA or like all this. Yeah, basically ALMA. You cannot really observe this guy with ALMA. That's why we have they use different observation. So this one they use NOEMA somewhere in Europe, I think. Not sure. Don't convert that. And then they measure the observation. So the sub-millimeter observation measure the CO221 emission line at the redshift of 4.85 with the beam size of roughly 2.7 arc second beam size. So like here is the beam size of the images. And then what they have reported in this observation is that they detected the continuum detection of the emission line here with the spectral index of 0.62, which is consistent with the optically thin synchrotron from the ASIAA. What? Okay, wait, sorry. So basically, what they have found is that the They have found that the molecular gas mass so they detected the molecular gas mass. So I'm not sure everyone familiar with the molecular gas. So when I talk about the hot gas, I talk about 10 to the 7 Kelvin gas. And then when I talk about the filament, so like the cooling filament that we detected in the optical imaging, that is roughly 10 to the 4th Kelvin gas. So like 10,000 Kelvin gas. And then, but star formation is only happen when the gas is cold enough, that is like 10 Kelvin. So like we basically have to cool all the gas from 10 to the 7 Kelvin gas all the way down to like 10 Kelvin for the star to form. So molecular gas observation is the gas detected as roughly 10 to 100 Kelvin gas. So this is a very strong evidence that this cluster itself have enough fuel or have enough cold gas to form the star formation that we have been detected in the optical spectra. And the molecular gas mass they estimated is 2 times 10 to the 11 solar mass, which is one of the largest they have ever found. And then what they have noticed is that the emission is pretty much circular near the center, but there is some extended or the northern clump up here. But this part is only 4% of the mass, and 96% is in the center of the clump. Okay, so in the paper, what they did is, they go through the scenario of why do you think this northern clump coming from. So here is they put the image of the galaxies here, the BCG and the filament, and then they put in the image of the molecular cloud that they have detected, and it's here with the northern clump up here. So the two scenarios that they are suggesting is that one of them is coming from the tidal tail, or that the molecular cloud or the molecular gas mass is got moved from the merging event, and that create the tail that are coming up here. Okay, or maybe the cold gas up here is actually coming from this. If you can see a little bit, maybe in the projector doesn't really show clearly. There is some very cold or like filamentary structure in the north of this, and some people think, or they also suggest in the paper, that it could be coming directly from the cooling of the ICM from the northern part of the cluster. And the cooling of the ICM create all this filamentary structure in the north, and also the green northern clump in the molecular gas. Okay, so either one of these could be a potential answer for this, but in this paper they have not conclude which one is which. Okay, so that is one of the paper that just come out recently that tell us about the amount of field that is available in the BCG, which allow the cluster of the star formation to happen. Okay, so the second paper is come from the radio. Then the first thing that they found in the radio is a milli-arc-second detection of the radio emission near the center of the cluster. So when I say milli-arc-second, here is the scale. This line here is 10 milli-arc-second, and they detected the emission up here. Also here is the beam side. So it's an extended object, but it's so small. It's like they call it a jet at 30 parsec scale. So we're now talking about a parsec scale jet that are so small in the center of the cluster. And then they also do it in multiple radio band, and then they also get the total estimated brightness flux density in each band, and then they saw the turnover here. And the turnover here tell you about the age of the radio jet. If the turnover here is coming early, so usually it's gonna go like this. So it should be a power law, right? So like normal radio jet power spectra just look like a power law, but is there a turnover here? That means the jet is extremely young. How young? We call it a gigahertz peak spectral radio galaxy, which the age of the jet itself is just 1,000 years or 10,000 years. So okay, now we have this picture of the jet is extremely young. Not only in the parsec scale, but here is the parsec scale that I just showed you earlier. But if you zoom out a bit more, in the kiloparsec scale with a different telescope called JVLA, they actually detect they call the radio whisker, which is So let me explain the observation. So here is the radio detection in kiloparsec scale. They think almost all the light here in the center is coming from the jet, but there is some of these I don't know what call it. They call it whisker. So like something that is poking out here, and they can this probably not coming from the jet because the jet is symmetric, like coming from both sides. It cannot really make this like weird looking thing here, and so they call it a whisker. It's roughly on the order of 10 kiloparsec south of the BCG. And then they think, let me show you the picture. They think that this whisker or like this weirded shape thingy is aligned with the filamentary structure that I saw in the optical with the filament with the Hubble imaging. Okay. So they think that this aligns with the Hubble star forming knot, which thinking that the radio emission that was detected here is coming from high star formation. So the star formation, the high star formation of all this filamentary structure in the optical, it actually creates additional radio emission on top of the ASIAA emission. And then if you do some calculation, so if you have a flux from the radio and you subtracted what is the expected jet flux density from this image up here, and then you say how much radio emission left that is around in this image, and then you convert how much star formation is needed to create that amount of radio emission, and then the star formation is roughly on order of 100 to 150 solar mass per year, which is consistent with what we found in the optical 140 to 190 solar mass per year. Okay, so yeah, so that is basically what this second paper have found. So what did we learn from the radio? The radio is very important because now we know, now we think we know that this CHIPS1911 is in what called a P feedback phase. Well, P feedback phase means that there is a strong ICM cooling, and that ICM cooling actually switch and turn on the jet or turn on the ASIAA. And the jet it just turning on with a tiny jet or like a young jet. And then because of that, then the star formation is still active because the quenching time scale of the hot gas is different compared to the star forming time scale of the gas. So the jet is just getting active, which means the jet itself doesn't have enough time to stop the cooling from happening, and the star is still forming near the cluster of the center or near the BCG. Okay, so this system basically we think is a merger-driven turbulence which create cooling instability, activate the agent, and then trigger both star formation and also agent feedback. Okay, so these are what the picture have been looking for now. So I'll summarize the whole thing at the end. But before that, because of so now that it's 2026. So now I have new result coming out with the Chandra observation. Okay, so let me give you oriented. So here is the image that I already showed you maybe 10 slides ago. I guess people already forget. So here is observation from Chandra for 30 kiloseconds. And here is the X-ray and here optical with the filamentary structure and but the important thing that I want to highlight here is that back then we think we saw two peaks, or like they are like I don't know why they are like extended peak or whatever this is up here, but here is the new data. So here is the data that we have got from Chandra for 10 times more than what we had before. Okay, so now you can see here is the extended or zoom out version, and here the zoom in version. You can see clearly this sharp edge. Yeah, I should not put the block, the green box here, but there is you can actually visually see clearly here the sharp edge. That is what is a signature for the core front. And then here is also another edge down here with a western core front. So yeah, so there's a western core front down here, and the eastern core front strongly detected here. And then when you do the contour plot, contour line of the X-ray emission, now there is no more two peaks. It's just one peak, and then yeah, there is a gap here. Yeah, some people think it's a cavity. It's probably not a cavity. I don't think it's a cavity. It's probably a spiral, or it's called sloshing feature in the cluster. Okay, so basically, if you can imagine, so the cool core here, so the cool core got moved. So it starts from here, and it got moved around like it's moving from here to here. Yes, but the key important thing here is that the cool core remains intact. What does that mean? Because usually when we think about disturbed morphology or disturbed cluster, the cool core itself should got heat up by the shock merger or the heat up from the other activity from the merging event, and the cool core should disappear or have a higher temperature or lower density. But in this case, it did not happen. The cool core remained intact and stay clearly detected in the X-ray. Okay, and so that's the location of the BCG, and yes. Okay, so what did we do with that? So with additional of data, we can do temperature map. So instead of doing just a profile, drawing a circle, and then kept going, and then you just go on. And now we can do a temperature map. So each one of these bins is one temperature. So yeah, we just run an algorithm to make sure that each one of these regions have roughly the same amount of count or roughly the same amount of signal to noise. And then the color here tells you the temperature. Down here is 6 keV temperature gas, and here is 12 keV temperature gas. And then the darker here is like 3 to 4 temperature gas, but it got cut off here. So you can see, first thing first, you can see that the center part here of the cluster is much darker in color compared to the outskirts. So that means the temperature of the gas in the center is extremely cold, which is why I call it cool core. And then we can clearly detect two core fronts. One here, if you follow my arrow, the blue arrow from here to here, you can see a big jump here in temperature profile. From here to here, yeah, we call that the eastern core front. and then from here to here is where the western cold front was detected. Okay, so that's it for the preliminary result. There are a lot more work to be done. I got a couple more ideas from this trip, so that I have to work on this observation. But before the end of the talk, I'll just show you the simulation that was done by the Karen group in NTSU recently. It got published this year actually. So here is a possible interpretation of what we have been looking for the entire time. So Karen ran a hydro simulation which show that when you have two merging subhalo, subcluster, and then the mass ratio is 3. So the bigger one is 3 times bigger than the smaller one. And then the impact parameter is not exactly 0. So 0 means it colliding head on, and then with some non-zero number, then that means the impact parameter is a bit further out. And then here is the central entropy, which is what I just talked about in the beginning of the talk. We tell you the amount of heat content in the center of the cluster. Usually, so in this simulation, they call it everything below this line, we call that a cool core cluster. And everything above this line, we call it a non-cool core cluster, or the cool core got destroyed. And here is time. So here is when the merging happened. So every cluster start pretty much in the cool core, and then I'm just gonna focus on the blue line. The blue line is one where the impact parameter is 464, and then is have the agent feedback activated, the blue solid line here. So usually all the other cluster merging scenario, you can see almost all of them, the cool core in the center got destroyed. The core entropy, the central entropy of the gas, it get pushed up very high, right? So much higher that it's not gonna come down to become a cool core for a while. Only focus on the solid line, because the dashed line when they remove the agent feedback. So in the solid line, in some scenario, it doesn't even gonna move down to become a cool core for a while. But there is one certain scenario that the cool core remain intact. And the cool core actually remain steady for the entire time of the merging event. And what we think is happened is that we think our observation from CHIPS is what is corresponding here. So the cool core can still remain intact in some merger scenario. Okay, so here is what a simulation of that specific blue line look like. So here's time from 0 gigayear, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, and here is two merger before it merging, and two subcluster before it's merging, and it's merging about 2 gigayear. You can see it's about 2 gigayear when it's merging. And then as it's merged, the blue is low central entropy, and then red is higher central entropy. So you can see these two cool core coming together, and as it's move, the cool core move closer together, then this thing stay intact. So like the cool core stay there, and then this thing actually got disrupted, or like the other cool core got disrupted, becoming the cold front, or like the not the cold front, sorry, the cold stream, or like the cooling thing. And then you can detect the thing inside, and then eventually then the thing settled down and it became that one cluster. So let me show you this picture. So I'm just gonna zoom into the center here. Let's zoom into the center here. Okay, so in the center here it's the same thing. Entropy, I have this image already. Entropy is here. The blue is low entropy and the green is higher entropy. So now you can see the core gas that is forming here. It actually create this long tail here that look like a structure with some eddy, with some turbulence here. And then what we think we see is that maybe this cooling filamentary structure, or like the Hubble filamentary structure that we see back in 2021, might be what we are actually seeing near the BCG here. That's what is the thing called, and that's why it's mostly symmetric in one, it's asymmetric, so it's only created in one side, because it's created when the cool core got moved, and then the other thing got deposit all the cold gas into the main BCG. And then if you zoom out or looking at it very carefully, there's this thing here, which is the radio jet. So in this simulation, they also predicted that there will be a young radio jet just getting activated in the center of the BCG, just by all this cold gas coming in from the outskirts or from the merging and create this jet, which is similar to what we see with a very young jet that people have detected in the radio.
So do you have a corresponding prediction for the dark matter distribution?
For the simulation, not
yes.
I have not looked into it yet.
Okay, so according to your interpretation,
Yeah.
so the system is after first passage.
Yes.
And but yet they are going to march again. They're going to experience maybe a few more passages.
Oh,
Settle that.
so I'm not sure. So I'm not sure whether it's gonna. The second core got disrupted. So I'm not sure. I'm not really sure. No, it's gonna like move that many times. It's not. So it's unlike the galaxy merger. The galaxy merger gonna come multiple times. But when the cool core, like the hot gas merge. Dark matter particle. Oh yeah. I'm not sure. We should take a look.
I think that's more important to understand.
I see.
Larger.
Or water dark matter.
Yes,
I see. Okay, cool, interesting. Yeah, I'm not thinking about the dark matter at all. So that's pretty much all the results. So let me give you 2 more slides for the conclusion, because everyone have been very patient. So the first slide for the conclusion, I'm just gonna summarize the property of what we have been detected in the observation. So we detected a layer system, which is a very strong cool core cluster despite this dynamically disturbed ICM. So like the large scale morphology is disturbed, but the center is very compact and dense. It's one of the most active star-forming BCG at redshift less than 1, with a large molecular gas detection, which is responsible or is a good strong evidence suggesting that the star formation that we have detected is probably correct. And then they detected in the radio observation, they have detected the young parsec scale radio jet, indicating the beginning of the AGN feedback, or it's just activating the AGN in the center of the BCG, but without affecting the ICM as a whole yet, because it still doesn't have enough time. So the proposed scenario of what is happening, or what we think is happening, is because of the recent off-axis merger, which displaced the secondary core, and but the primary cool core still remain intact without got destroyed. And then that merger actually induced mixing, which is actually not sufficient to stop relative cooling. So like the cooling is still happening, but then it also but then the AGN also doesn't have enough time to heat up the gas. So it will continue cooling and ICM condensate to fuel both the star formation and the AGN activity. Okay, so I've been spent a lot of time talking about one specific cluster. Why do we care about this one specific cluster? First it's very nice, but most importantly, because even though the reason that it matters is because now we have a strong evidence that the strong cool core can actually survive the merger event, which is consistent with recent hydro simulation. Even though, so when Heren was published the paper, she haven't found any like optical example that looks similar to what she found in simulation. So we could say this is one of the first evidence for that. And then it also tried to focus on that the limited merger-induced mixing allow relative cooling to continue, so the cool core still remain intact because even though it got moved around a bit, but because of the merging geometry or merging ratio of the two subhalo in such a way that it's perfect that the cool core still remain intact, which allow a large amount of cold gas to coming into the agent and actually activate the agent feedback. And which also allow the cooling to form new star and create a high star formation rate, BCG, in the center of the cluster. And the very last sentence is what I try to emphasize, is that even though this is one of the rare systems, we don't think that every cluster, let me say that again. So we think that these are just a very short period of time of what is happening to many clusters. So we don't think that in only this specific cluster that this scenario is happening, but instead we think that when the merger happens, some of them have this property too, but the runaway cooling phase is extremely short. So you can see here, the cooling phase part is only lasts for like 1 gigayear, and then everything else just look like or got destroyed or is before the merger. So we don't think it's extremely unique in the sense that not every galaxy will go through it, but we think it's unique because it only happened to a very short period of time of the cluster lifetime. That's why it's difficult to find, and that's why this one is a good example of what we can learn just by looking at one object. Yes. I think that's it for my talk. Thank you.
Any questions?
Thanks for the nice talk. I have a couple of questions.
Okay.
Go back to the slide where you had radio observations.
Okay. This one or this one?
Yeah. Do we know the spectral index at the higher wave?
This part, higher frequency. In the paper they reported the spectral index, but I did not put it in, and I don't remember. I think it's pretty similar to a typical radio agent spectral index, but I don't have the number.
Spectrum source?
I don't think it's super steep, no. Yeah. So I think from what I understand is in radio, if it's very steep, it means a very old radio jet. Yeah. But this one is very young, so it's not very steep.
But like this object is still classified as a GPS source, right?
Yes.
And like GPS sources also have a very similar person called CSS, compact steep spectrum source. Would it still be classified as a CSS?
Oh, I see. Good question, and I do not know the answer. Yes. So so from what I understand, from what I talked to the radio people, is that because of the GPS source is very small and compact, then what I saw, what I understand is because of the turnover here, that's why they can estimate the age. But yes, I don't know whether we can classify it as CSS source as well.
And like very quickly, if you know the radio background, like I'm not sure like how we get the star formation rate with the radio observations.
Oh yeah, I don't remember the equation. So yeah, so what they did is they have the total power of the radio emission, and then they draw the expected brightness of the young agent jet, and then they calculated what is the radio emission coming from the star formation, and these are these two dots, and then from these two dots they converted that to the star formation. But yeah, you still have to look at the paper to see which equation did they use.
So it is possible to just get just with radio data to estimate the star.
Yeah, so they just estimate star formation. But the problem that not many people do it. It's actually very difficult. Is because almost all the emission coming from the radio agent. The reason that they can do it in this object is because they have two observations. One in very high resolution radio imaging, and then one for the bigger kiloparsec scale imaging. And by having both, then you can have an ability to distinguish between the radio emission coming from the agent, and by subtracting that, then you can get the the radio emission coming from the star formation. But you can see it's like one order of magnitude smaller in flux. So yeah, it's not easy.
And like, I think you stressed this at the last few minutes, but is it the only example we have where we have actually documented image or like an example that shows that it is a source with star formation happening, but also like the radio AGN jets have also just initiated? Is it the only unique example?
They have with the same author, I think they have found a few onset AGN observation, but some of those systems doesn't have a lot of star formation. So I think recently there was one by White at 2025, I think, we found an onset on one of the SPT cluster with also called a young jet, but I don't think they have a lot of star formation in that one.
So this might be very unique.
Yeah, so it might be very unique too. Yeah.
Another general question. Will you show some of the low temperature BCGs? And all the low temperature BCG sources does not have aging?
Yes. When we talk about AGN, so there are like different type of AGN. So if it radio AGN, usually about 30% of the cluster have some radio emission in the center of the BCG. 30%, 30. Yeah. I had a detected radio AGN. But if we talk about like the X-ray AGN or like the mid-infrared AGN, those are roughly like from 5 to 10%. So it's very small to detect that like the actual AGN emission forming the BCG.
Those 30% of
Yeah.
the radio AGN, that's AGN is not strong enough to warm up the temperature at the center.
Oh, so those 30% we think is strong enough. So those usually the cluster in those 30% AGN with radio jet does not have a lot of star formation. So the BCG look like elliptical galaxy with no star formation or no cooling. So yeah, we think the radio emission is enough to stop the cooling and heat up the gas. How did I find the distance?
Yeah, how did you find this system?
Oh, this system. Okay. Ooh, good question. So this is the CHIPS survey is starting because we started from the X-ray point source. So the idea is in the past I used lowest, so like really long time ago. So like the lowest catalog created the point source and extended source. So all the extended source are galaxy cluster, and then all the point source they call like a AGN or compact object. But what we found is that a lot of the point sources that they call point source is actually a strong cool core system, because the cool core is so peak in the center. So what we did is we go back to lowest point source catalog and cut out all the most massive or like the brighter one, and then we try to see which one have the optical cluster detection. So like over then of galaxies, and then we use X-ray follow-up to confirm the cluster.
Okay, so it's based on X-ray. Start from the X-ray observation.
So start from X-ray point source, confirm by optical follow-up, and then use the X-ray to confirm again with the Chandra.
Yeah, I'm curious because for the optical observation for the cluster finding mostly based on the color of the galaxy.
Yes.
Colors. I wonder whether or not this kind of algorithm will miss this.
Yeah, it will miss it. So almost all of this system and also this system have been missed by almost all of the optical observation, because the BCG doesn't look like a BCG at all. Yeah.
Thank you.
Any other questions?
There's a plot for peakiness and disturbed ICM.
Oh, yeah.
It seems there are still a lot of objects in the
On this side? Yeah.
Do you expect them have similar behavior, or do you plan to follow up?
So from what I understand is that almost all of this doesn't have too much star formation. So that's why we have not do the follow-up on. But yeah, it would be interesting to see what they are look like. But yeah, we haven't really done a ton of work on those systems. Yes. Thank you.
Any other questions? If not, let's thank the speaker again.
Thank you.